I do not.
But,
We just hit, okay.
yeah, but we make exceptions when there's a particularly good talk that we want it to be on internet forever. And in this case, Rahim's talk.
Thank you.
Yeah, let's get started. This is Deep Learning Classics and Trends. I'm really excited to hear about this paper. It's from your internship at UW, Rahim. You're so productive. One paper per internship, that's not guaranteed these days.
Yeah, thank you, Roseanne. Thank you for having me, and hello, everyone. So I will be talking about this paper, which we put it on archive like 2-3 weeks ago. As Roseanne mentioned, that was a team effort while I was in University of Washington, Seattle, with Ludwig Schmidt and also Mitchell Wurzman from UW. Also, other teammates are Olga, who is my supervisor, Ania Sedri, who is in Google, and also Moin. So we have a very diverse teammates from Iran, from Google, from University of Washington, and from Vienna. So the talk will be about the role of pre-training data in transfer learning. So when I started to look at the literature on the role of data, I come up with like tens of papers. These are some examples of these papers. Maybe one of the most well-known is Simon's paper, Do Better ImageNet Models Transfer Better. Also exploring the limits of large-scale pre-training. So there are lots of papers who are trying to answer some questions regarding pre-training and transfer learning. But actually, there were some really research questions that I couldn't find the answer to. One example is, what is the role of pre-training data distribution and transfer learning? Like practically, I have a target task, let's say CFAR10, and if I go to Hugging Face, I have tens, thousands, maybe checkpoints to download and then pre-train, use this pre-training and then fine-tuning on my target task. And I had like a very simple question, which one I should choose? And I really didn't know that.
And I try to answer it in a stupid way.
Yes.
Just every data out there, the more the better. Yes. Isn't that our current?
Yeah, probably not. Yeah, I will show you the results later.
Okay.
The second question was that out of these tens or hundreds of like checkpoints, some are like supervised pre-trained, some are semi-supervised, more data, less data. Which one should I use? Like, what's the value of expensive leveling? Do we still need supervised ImageNet, or it seems that the recent trends are going for more and more data, but less supervision? And the third one is, of course, what's the effect of scale? We see this, we are going more and more. How does this trend look like when we go for transfer learning, not zero-shot transfer? So let me begin with the experimental setup that we did. So just as a disclaimer, this paper is totally like experimental paper, and we are going to look at careful design of experiments, which I really enjoyed, Mitchell and Ludwig. So with pre-training data set, we looked into 6 different data sets, actually plus 1, which is ImageNet. Starting from LAION, YFCC, Wikipedia, conceptual captions, RedCaps, Shutterstock. And all of these data sets are from million size scales, except for LAION, which is recently a 2 billion, 5 billion, but we use only 15 millions of samples. And they are crawled from different sources, including like Flickr, Common Crawl, Wikipedia for Wikipedia and Shutterstock web. And these are some examples for images and text. Yes, Roseanne?
Well, we're talking about just vision data sets, right?
Yes. So these are multimodal data sets, text and image data sets, and all the downstream tasks are vision data sets, which I'm going to show you later. So these are some examples of these data sets. This is just a quick example, like 8 different images and text pairs from LAION. You see, maybe the captions are not very clean, but they are somehow good enough to work with. For conceptual captions, they are much more noisier. So these different 6 pre-training data sets vary a lot in terms of quality of the text and also images. Like the image and text pairs are completely different from one data set to another data set because they were crawled from different sources. Like conceptual captions were from a lot of web pages. If you go for the paper coming from a lot of papers, and LAION is from Common Crawl, and like Flickr for YFCC. And regarding the target data sets for this paper, for the sake of this paper, we looked into 9 different target data sets, starting from CFAR 100, DDT, Caltex, PETS, which are very well known in computer vision, also DomainNet Real and ClipArt, which are somehow famous, plus another 3 data sets, which I'm going to show you some examples, like camera traps, CasaLeaf, and Eurosat. Like if you're not very familiar with these 2 data sets, on the left, you see the camera trap. On the right, this is CasaLeaf. Like as the name suggests, camera traps are camera images from the wild, like from images during like day and nights in 15 classes, and the number of samples are only 60K compared to pre-training, which has millions of samples. On the right, you see like natural images of leaves, healthy versus 4 other classes, like in total 5 classes, 21K samples. So the difference between the last 3 and the first 6 is important to note. Like the first 6 are the data set which has been there for a while, and then machine learning scientists decided to solve some problems out of these data sets. But for the rest of 3, there was a problem. Like let's say there are some animals on the in the wild, and we want to distinguish between different classes. So the expert, like animal expert, decided to put some cameras on the wild and then track some animals. So there was a problem, and then they decided to capture images. While for the first one, which are mostly crawled from internet, there was a lot of images over the internet, and then people try to classify or solve some problems. This is a very important detail, which most of the time people neglect. That's like the pre-training data set is common crawled like from the internet, but the downstream is coming from the domain knowledge, expert knowledge. We need to take care of this similarity between pre-training and the downstream, and I'm going to show the results. Why is that important? For the pre-training method, we use Clip and SimClear because we are going to, and also Supervised, which is not here. So different supervision, like Supervised, let's say ImageNet, Clip contrastive language imager, SimClear, which is also semi-supervised only on image modality. For fine-tuning methods, we just grab a pre-training, and then for fine-tuning, grab a pre-training that we already pre-trained, fine-tune it using like full fine-tune, which we already know it, like it converts. Linear probe and then fine-tuning, which was a paper like 2-3 years ago, which is an improvement to full fine-tuning. And the difference, who are not familiar with this LPFD, is that when we do full fine-tuning from scratch, let's say just I'm going to make an example. So if the pre-training is ImageNet and the downstream task is CFAR 10 with only 10 classes, we have no choice but to add like to remove this fully connected from ImageNet pre-trained, and instead of 1,000 neurons, now we have 10 classes because the downstream is CFAR 10, and we need to initially randomly initialize these 10 neurons, like the connections to the previous layer. That's full fine-tuning. What LPFD does is that, like, now it doesn't make any sense to randomly initialize. Maybe it's better to initialize it better. How? By now make it in 2 steps. Like we add these 10 neurons by the end and only train this the last layer. So we freeze everything except for the last layer in the step 1. We call it LP, like linear probing. And now after it's like already converged for who knows how many epochs, and then because it's like linear probe probably will converge soon, then we have a nice initialization now to do this full fine-tuning. So this is a 2-step full fine-tuning, which does better than full fine-tuning. And not only full fine-tuning, but also like this could be divided into using all samples and fewer samples, like few shot versus full shot. In full shot, as I just described, we use all samples from the downstream task, let's say CFAR 10. But in few shot, we use only 1 sample per class for 1 shot, or 5 samples per class, like 5 shot, and etc. until we are going to use all samples from the downstream task. So we are going to cover all these different experiments. You may also already notice that there would be thousands of experiments with different hyperparameters. But it's worth noting that like I couldn't find such a like experimental design to the best of my knowledge in the previous work. So mostly they were comparing oranges with apples. But if you want to capture nice like observations and conclusions, you need to cover probably a lot of settings and take care of your question. So if the question is only supervision, you need to keep everything fixed except the supervision, like data distribution, everything, like the algorithm, pre-training algorithm, everything except the supervision. And you will see this careful design in the next slides.
Can I ask a question?
Yeah, sure.
So there's what, 1, 2, 3, 4, 5, 6 pre-trained data sets. Are you doing experiment with one of them at a time, or you always combine all of them?
No, for the combination was a good idea, which we didn't do this. Like you could also randomly sample 1 million from Shutterstock and also combine it with another one. Actually, another person from the University of Washington already did this, but for this paper, we just isolate one pre-training, get pre-trained, let's say on LAION for how many epochs, and then get the checkpoint and then fine-tune it on Cypher10.
I see. So total experiment number is like pre-trained data sets 6 times target data set 10 times 2 pre-trained methods and like 4, at least this much.
Yeah, and times 10 or 100 because we need to also take care of learning rates, number of epochs, batch size, etc.
That's impressive.
So we did like 3,000 or 4,000 experiments, which I'm not proud because this is not very sustainable, but I couldn't find any better ways to do this. At least we did it for once and we have nice conclusions. So maybe in the future, people do not need to do this from scratch.
Also a question about the pre-training method. You use clip and SimClear. So with clip, you would train the image alongside their caption. Does every image have a caption?
Yes, for the ones that I showed you, yes. Okay. For the pre-training like LAION, BiFCC, all of them are multimodal data sets.
I see.
And for those who doesn't have like ImageNet, I'm going to show you how we did a trick to make it like clip friendly.
Okay. For SimClear, you don't need the exact caption. You just need to know if 2 images are from the same class or.
Yes, SimClear, naive SimClear, you don't even need that. Right? You just need an image modality.
Okay, thank you.
Okay, so let's get back to the first question. What's the role of pre-training data distribution? So given a target data distribution, now we want to find out which of the pre-training data like choices is best for our case. So let's say our target data distribution now is Cypher100, and I have 2 choices like conceptual captions 3 million and LAION 3 million. So conceptual captions 3 million actually has 2.7 million. So we fix everything. This is just an example. We fix everything except for data distribution. Like downstream is already fixed to Cypher100. Pre-training algorithm is now clip. Number of epochs, everything is fixed except for data distribution. And my question to your audience is which one of them you would estimate that's happening? Like if you just grab conceptual captions and then fine-tune it on Cypher100, let's fix it to 100 epochs. So you use all samples from Cypher100. Do you believe that LAION and conceptual captions would perform similar, or LAION would be better, or conceptual captions? 1, 2, or 3? You can write in the chat.
Which data set is closer to Cypher10?
Can I choose both? Would both be better?
I got 2 questions. Like Rosanne said that we need to find out which one is closer, which is a nice start. And the other one, who was? Please speak up again. What was the second question?
I was saying, how about using both? Wouldn't just using both be better?
Yeah, of course. I'm not sure if both is better, like the combination of both. But for now, just let's say that I do not have enough resources to train on 6 million or a combination of both. But just the question is that which one is better? I have only one to choose one of them.
Isn't CC3M actually really curated? So I would say it will have more effect on downstream tasks. Because
so
LAION
both
has
2.7 million. So this is called conceptual captions 3 million, but
yes. So LAION has so many duplicates and like CC3M is really curated, at least from my end.
These are very good
I would
points
say,
to look at. I should say that I'm not the expert to know what's going on inside of each data set, but experimentally, I will show you which one is happening, 1 or 2 or 3. But this is very nice, good point that there might be some duplicates, there might be some similarities between Cypher10 and LAION, more than conceptual captions that we need to take care of. Another question that I had, that I needed to run many experiments, is that, let's say for full shot, this is happening, 2 is happening. Then what happens if I go to like 5 shots? Again, 2 is happening, or that would be flipping. So that was another question that I had, that I will show you the answers in the following slides. And the third one that I'm going to ask you, like at least think it for a couple of seconds, is that like we already said that like let's pick conceptual captions that would be here. Then the next question is that what would be trend from? So if I change it on the y-axis, the number of shots from 1 shot to 500 shots, how would you see the trend? Is it like a linear trend here, or is it like saturation very fast here, or it would be saturate very late here? So that was the kind of questions that I had, that I couldn't find the answer in the literature. And why we looked into few shot, because it's very important. Like in maybe most famous example is medical domain, which we do not have enough images per class. That's why we were interested to look into also the number of shots, not only full shots, which in the case of Cypher10 is 500 multiplied by 10, that would be 50K, like 5K Cypher10, and for the other one is 50K, see, for Cypher10 and 100. So we needed to look into different number of shots: 1 shot, 5 shot, 10, 20, 100, 200, and 500. So that I had these 3 main questions in the case of Cypher 10 or 100 to answer, and we are going to answer this. Okay. So,
wait, why is full shot 500?
So we have this is CFAR
100.
That was CFAR 100. Yeah. So we have 100 classes, 50K samples. So for each class, we have 500 samples.
Oh, this is per class shot.
Yeah. This is shot. This is called shot. Right? Number of samples per class.
And then the final evaluation is on the holdout, like 1,000.
Yes, on the
samples.
test. Yes, 10,000. Yeah.
Okay.
So this is what I observed. So no matter what the pre-training data set is, if we go for full shot, there is actually no difference between this pre-training data set, which was surprising for me. That was case 1 in question 1. So you really do not need to worry about this. So if you choose conceptual captions or shutter stuff. And for your reference, this is the training from scratch without any pre-training. Of course, I was expecting pre-training to be better than training from scratch, but I didn't know that how much it would be better. And this is the difference for the case of C400.
Wait, so full shot, but which method? Is it training everything or only the linear probing layer?
So here is a full fine-tuning. I'm not sure if I have the slides for linear probing or if you have time, probably in the backup slides, but this is for full fine-tuning. Okay. Linear probing is to compare with SimClear. Clip and SimClear, because we need to make it fair. You can go to look at the paper, but for the SimClear, because we needed to make a fair comparison, we need to also include linear probe and full fine-tuning.
I don't know if it's just me, but I'm surprised the gap is so small.
Yes, I was also surprised because everybody says that like training from scratch is way worse. Let's do this on pre-training. If you have enough data on pre-training, just do pre-training and then fine-tuning. But the gap is really small for C400, at least for these data sets. And it's just one note here that all of these data sets has only 3 million samples, not 10 or 15. Yeah. Compared to LAION, 5 billion is not that much.
Is it a ResNet or like a?
Yeah, that was also a good question, right? All of them are ResNet. Backbone of Clip is ResNet. And if you have in mind why 3 million, not 15 million, because I just wanted to include all of them. Like conceptual, like Wikipedia, for example, has only 5 million. The rest are 11 million, 6 million, something like this. So I chose 3 million for basically 2 reasons: to make 6 or 7 data sets pre-training to compare. And the second reason was that training on 15 million, like pre-training on 15 million, is like needing more and more resources, GPU power, to pre-train on 50 million rather on 3 million. I pre-trained on 3 million and then fine-tune on Cypher. The second question was that on the trend. So this is the trend here that you can see. So the main observation is, of course, the x-axis is not linear, but like that would be logarithmic, because if we change the x-axis, but that was case 1 or 2 that I previously showed. The most important observation here, takeaway message, is that like as you move on the x-axis from the left to right, you see that the difference between best and worst pre-training shrinks. So it's very important to choose your pre-training data set if you have only 1 sample per class, and it's almost same everywhere. Like Shutterstock is this one, these hexagons here, is almost best everywhere. But the important part is that the difference is really shrinking. So if you have 10 samples, it's important. And interestingly enough, Shutterstock is doing well on most of the data sets, which I'm going to show you later. But it was interesting to see this shrinking as we have more and more images. Let's go for more and more data sets. Like these are now the rest of the data sets from DDT to Eurosat. So again, the observation holds. The main observation is that as we move from left to right in the x-axis, the difference between best and worst shrinks. For some of them, it's only 1 point, like real. And the reason being is that for real, we have like 350, while for DDT, we have only 40 samples. So again, if you have enough samples, and enough means that 200, 300 samples per class, then ultimately there is no difference between pre-trained data sets. But you have less, it is important. And I'm going to conclude it in this nice visualization. Right here, you see these violin plots. And these violins are the difference between best and worst pre-training. So let's say for this case, the worst was Wikipedia, this blue triangle, and the best was Shutterstock. So here, if I'm just going to make an example, on the x-axis, number of shots, let's fix it to 20. And for these 20 shots, now I'm iterating over different pre-training data sets. Okay, so pre-training conceptual captions, again, 3 million, another random subset of conceptual captions, red caps, etc. And if you look at C400, so you fix the pre-training data sets to Wikipedia here, you fix the downstream data set to C400, this is the accuracy that you will get. Again, if you change the pre-training data sets, the best would be LAION, which is 50 something, and 40 something. So the difference would be 20%, right, between best and worst pre-training data set. And again, if you do it over DDT, that would be around 15%, and etc. Right? You did it so on and so forth. So if you just get the average out of this best minus worst and normalize it, that would be this violin plot. So the main takeaway message here, as I just mentioned previously, if you have enough samples, more than 100, 200, 500, even 3,000, then the difference between worst and best pre-training data set is negligible. While if you have less, around 50 samples, it is important which pre-training data set is better. Like, let's look at one of these examples. Like, we just noticed that, like on pets, this is the pets downstream. On pets, red caps, which are these green squares, are doing better. And we just had a question, why is that so? Like, why red caps is doing much better than the rest? Like, Wikipedia is way worse than red caps. So we looked into random samples of pets on red caps. So pets, as the name suggests, are pets. We looked into red caps, and these are red cap samples. Look, there are many pets here, right? Snake, dogs, cats again. And these are just random samples. Like, if you just look at random samples of red caps, there are many pets. So visuality, so as Roseanne just noticed in previous slides, it's very important, the similarity between pre-training and downstream task. In this case, red caps is very close to pets. That's why red caps is doing best. So again, if you have enough samples, you do not need to worry on the downstream task. But if you do not have, like if you have only 100 or 20 samples, then you need to look at the similarity, visual similarity between pre-training choice and the downstream that you had, and you need to solve. Not only this, but also we looked at the text similarity. Like if you look at like red caps for top 20 words in random samples of captions, red caps has some words like cats and dogs. These are inside the captions. While for the rest, this is not happening for the top 20 words. So I do not see any words like animals in the red caps captions. So red caps was closer to pets, not only in terms of visual similarity, but also in terms of text similarity, which we know it as labels. So any questions so far? If not, I'm going to show you another example. Like this is DDT. So on the right, if you're not familiar with DDT, these are examples from DDT, describable texture dataset. These are some textures. I really don't know the names, the name of these textures on the right. But we just noticed that Shutterstock, which is this red hexagon, this pentagon, right, is doing best compared to the rest. And I wondered why is that so? So if we looked at like Shutterstock examples, let's only look at the text. You see some words like background, design, pattern, texture in the top 20 words of Shutterstock. So it was very important to have clean, let's say, or closer captions to the downstream datasets. So again, practically as an ML engineer, if you have some dataset and you don't know which one to choose, which one pre-training dataset to choose for transfer learning, you need to look at some samples of your pre-training dataset and probably have some idea which one you need to choose. Okay, any questions regarding R1, research question 1? So research question 1, takeaway message, like it was about which pre-training dataset, which pre-training data distribution I should choose, and we talked about similarities to downstream tasks if you do not have enough samples. So the next question that we had was supervised versus self-supervised or contrastive, let's say in the case of CLIP. So let's begin with supervised, which at least I feel most comfortable with. So for supervised, let's grab a supervised ImageNet pre-training using ResNet 50 from the web Hugging Face, and then fine-tune it on C400. These are the results that you will get as number of shots increases. This is our baseline, and we are going to compare it with contrastive step by step. So now, as we are dealing with ImageNet, and we do not have captions for ImageNet, and we want to compare it with ImageNet, like we want to train CLIP on ImageNet, we need to somehow create some captions. So again, into like careful experiment design, we need to fix everything except now the data distribution, right? So data distribution here is ImageNet. We need to make it somehow CLIP friendly. So we had some choices. The option 1 is to get the original ImageNet captions. Like in 2010, people crawled ImageNet, created ImageNet, and a good portion of ImageNet is crawled from Flickr. So we just use this 500,000 size. Like we know that ImageNet, at least the 1 million size, half of them are coming from Flickr. So we could get original ImageNet captions, which are not very clear, which are not very clean, but at least we have access to that. So if you just want to compare with supervised, this is the CLIP pre-trained on 500,000 size of original ImageNet captions. Okay, so supervised was much better. Again, if you have enough samples, on the case of CFAR 100, which is this case, if you have 500 samples, it's not important which one you choose. Either pre-training from ImageNet supervised or CLIP contrastive from 500,000 size of ImageNet. Both goes to 80 to 3%, which was interesting to see. One may say that these triangles, blue triangles, are trained on 1 million samples, while these stars are 500,000. So that's probably, we need to do some ablations here, right? So this is half the size of the data set. We changed both the captions, like the pre-training algorithm, which is supervised versus contrastive, and also the size. We also need to remove the sizing effect. So that's what we did with the option 2. So we created like synthetic captions, like we call it template captions, like OpenAI clip paper. So one way to do this is to use labels as a sentence. Like, this is an image of a dog. This is an image of a cat. So in this way, we have ImageNet, we have 1 million images, we have class labels. Now we can create captions, clean captions, and now we can train clip, pre-train clip, and then fine-tune it on C400. Now we see that if we have enough samples and clip and like clean templates, like clean captions, we can catch the ImageNet, like supervised pre-trained ImageNet. That was surprising to see, because now we do not care about what pre-training method we use. No matter if it is contrastive semi-supervised or supervised, we can get almost same accuracy. In some cases, like contrastive is even better than supervised pre-training. And yes, is there any question?
What is the effect of multimodality in this? Because the clip is trained on both images and text, whereas your supervised ResNet is trained on only images. And generally, like when you train a system in multimodality fashion, it kind of improves the performance.
Yeah, so you see the observation, right? So it seems that multimodality is because we fix everything. Let me check. So we fix data distribution, which is ImageNet. So the only difference between these 2 points is the contrastive loss function, which includes the multimodality. So I see no other reasons but the one that you just mentioned to be better than the supervised.
Okay.
But people already showed that like the success behind the clip, OpenAI clip, is not the contrastive or multimodality or even language supervision, but it's data distribution for the clip case. But here we fix everything except for pre-training.
Okay.
algorithm.
But the clip was trained on, I think, 400 million.
Yes, 400 million, yeah. For
It
that
was
case, the
too
distribution.
huge, so.
Yeah. But for this case, we fixed data distribution. The only difference between these 2 points, this one and this one, is the pre-training algorithm or method, which is contrastive in this case, and the other one is supervised.
Okay. Interesting to see. Thank you.
Sure.
Could you go back one slide, please? Yeah, so does this gap between supervised ImageNet and Flickr keep increasing as the number of shots increase beyond 20 as well? Because it seems as if for 1 shot to 20 shot, the gap between the accuracies is...
Yeah, I haven't done this between 20 and 500. That's a good question, but I do believe that that will shrink up until, because here it's 0. So at some point that will go up and down, like double descent, 1 descent, something like this.
I see. Would you happen to know why it's increasing in the first few, at least till the 20 shots?
Yeah, it's very hard to do this. Like if you have only 1 sample or 5 samples, these are not very reliable, I would say. Like if you just do this pre-training only and then fine-tuning only 5 samples without any clean labels. Consider these stars are very noisy captions. And then you want to fine-tune it on C400. So that would be a bit challenging.
Makes sense. Thank you.
So the takeaway was like contrastive to some extent was even better than supervised up to some shots. And then ultimately the difference would disappear. So from research question 1, you already seen that data distribution is not important. Now you already noticed that like also the pre-training algorithm is also not important if you have enough samples for your downstream task, which was surprising to see. So let's change the data distribution. Now we want to compare ImageNet with LAION to see what's the effect of data distribution, like the research question 1. So let's compare LAION with ImageNet Flickr. Both has 500,000 size data sets. The only difference between them is data distribution. One is LAION, the other one is ImageNet data distribution. And we see that LAION, like ImageNet, is doing like very small, but it's still doing better than LAION. Just to compare, if you just double size the LAION samples, it could catch up the ImageNet data distribution. So it seems that something is happening with ImageNet. I don't know how they crowd it. To some extent, we know it, like from Flickr, a good portion of that, but at least up to 1 million ImageNet data distribution is twice nice compared to LAION dataset, LAION data distribution. So it's twice worthy as LAION data distribution. Let's compare it with the ImageNet clip captions, like clean captions, I would say, and see that's like the quality of the clip captions is very important. So if you just compare these hashtags with this same image with these squares here, because I want to fix everything except for except for the quality. So here the hashtags are ImageNet clip captions. The hashtags are ImageNet clip captions, and the scores are LAION 1 million. So size is 1 million, but data distribution is also different. So you see that data distribution really matters from ImageNet. If you have clean captions, which are, this is a class of doc, that could be like a supervised pre-training, and that could really boost the pre-training, the downstream performance. And if you have more data, because we have from LAION up to 5 million, we can include more data. So you can see that without any clean labeling. So the only difference, the difference between this cross and these hashtags is that we do not care about any clean labeling. So if we just crawl 15x more data, then you can catch up with clean labels. And just for a reference, this is a supervised. So that has a message to people in 20,000, like 10, when they crawled ImageNet, that you do not actually need ImageNet, a lot of supervision and a lot of human power to make it. If you just crawled 15x more data, like LAION, then at least for the case of C400, you could catch nice performance, which was also interesting for me to see.
But back then we didn't have good contrastive learning methods.
Yes, yes, yes. Not only that, but also I was very surprised to see this, and let's look at other data sets. So this was C410 that you already seen, but that wasn't the case for the other data sets. So the blue ones, just as a reminder, are supervised. So supervised on ImageNet is still doing better on DDT, on Caltech, on PETS, on Real and ClipArt. So the only example was C400. So it's still supervised ImageNet was doing best for other data sets. So people should be happy to crowd ImageNet and label it. And it's still doing much better for the case of Caltech. And look at PETS. Like PETS is doing much, much better than 15x more data of LAION. And the reason is probably being close of ImageNet to PETS. You already noticed that like ImageNet has 200 classes of dog breeds. And that's a lot of animals in ImageNet. 200 out of 1,000 classes of ImageNet are dogs. That's probably why ImageNet is doing astonishingly well on PETS. That was on 15x, LAION 15 million. What about LAION 2 billion? Because we have. So let's compare 2 billion now. These circles are now 2 billion. Okay, ultimately we can catch up DDT and ClipArt with 2 billion more data. Like these are LAION 2 billion and these are supervised ImageNet. You see, like we need 2,000 more data to catch up with supervised. It's really like either it's because of ImageNet data distribution or it's because of supervision. We already seen that supervision is not important. So it seems that like ImageNet has something like a magic in this data distribution that we had 2,000 more data, like 2 billion more, almost 2 billion more data points to catch up with supervised pre-training on ImageNet. However, again, that wasn't the case for the rest. So for some cases, again, 2 billion more data points is not enough. So again, for the case of PETS and Caltech, again, supervised on ImageNet was getting better results. So I'm going to make it faster. So the last question that we had was, transfer accuracy as pre-training size scales. So here we compared YFCC 2 million with 15 million. Of course, 15 million should be better, as we already noticed, like these triangles are better than crosses, which are 15 millions, 5 times more data. But interestingly enough, no difference if you have enough, again, samples. You do not need to include more and more data if you have enough samples for the downstream task, which is in this case C400. Same for LAION. So comparison between LAION 2.7 million with 15 million. Again, of course, 15 million is better when you do not have enough samples. But if you do have enough samples for your class, which is more than 200, 300 samples per class, then you do not need to worry not about the data distribution, not about the supervision, the pre-training supervision or algorithm, and pre-training size. That was surprising to see. And what about if we have 2 billion now data points? That was comparison between 2 million and 15 million. And now if you have 2 billion, then it really makes sense. So 2 billion is now better even if you have 500 samples per class. So LAION 2 billion is like around 8 to 10% better than 15 million samples or 2 million samples. So if you could get checkpoints from Hugging Face, which are already trained on 2 billion, 5 billion, then it really makes sense for not only full shot, but make a lot of sense for one shot and probably zero shot. That's why people in the community are trying for more and more. So not only for zero shot, but also for transfer learning, we see that it really makes sense to have more and more data. And by more means billion size scale, not million like this one. And what about the other data set? That was also the case. So the C400, you also see that like C400, if you have enough samples like for full shot, there is a difference between them. For DDT, there is. For Caltech, there is still a little bit of difference between 15 million and 2 billion, but that should be negligible. Clip art also very close. Real is also close, and pets. So maybe the best example of the difference is C400. Not all the rest, again, it doesn't matter how many of samples you already trained, pre-trained, 2 billion or 3 million. Yeah, so let's conclude to 3 points, main takeaways. So what we discussed is that the changing pre-training data sets leads to noticeable differences in few shots, but if you have enough samples, it's not important. Like pre-training data distribution is not important, pre-training algorithm is not important, and also pre-training size up to a couple of millions, maybe 100 million, it's not important. We already noticed that the specific data sets like Shutterstock performs well on almost all studied tasks, like these pentagons, red pentagons. And it seems that people at Shutterstock are doing some magic stuff there. I already heard that they are making some deals with Meta, if I'm not mistaken, or OpenAI. So I don't know how they crowd it, and probably they are not very willing to share that. But Shutterstock is doing much better, at least for these 9 different data sets, including the natural ones like camera traps, and also well-known like Sapphire 100. Shutterstock was doing best on all cases, almost all cases, except for pets, which was red caps. So, and for some cases, again, back to 2010, we almost can get everything with all of these downstream tasks with more and more data, except for some cases which we need like 2,000 more data, maybe 5,000x more data. But it seems that like people at 2010 did some magic stuff with ImageNet crawling and also with labeling. So again, I think that labeling, like the main takeaway message for me is that data distribution is very, very important when it comes to transfer learning. It totally depends on the similarity between pre-training task and also the downstream task, which was not surprising. But what is surprising is the power of labeling and the image, like the data distribution crowding from the internet. The next time people are trying to crowd the internet, people probably will spend a lot of money on labeling and also careful crowding. Yeah, that was it from my side. Thank you. If there is any questions, let's continue discussing.
That is a lot of experiments.
So we did 4,000, 5,000 different experiments.
This is the type of paper that I'm just so glad someone did it, because I can't even imagine doing it myself. There's so much pain.
Yeah.
It's like a giant spreadsheet to even keep track of all the experiment results.
Yes, yes. And everything is accessible through my GitHub. I do not have the link here, but the spreadsheet is available there with all learning rates, hyperparameters. So let me know if you need any checkpoints I can give you. So please do not retrain all these models. And I just skip the SimClear experiments. It's already in the paper to compare SimClear and Clip. But again, what is important regarding these experiments is to compare oranges with oranges, which is, I would say, which is not the case most of the papers. In most of the papers, they change apples and oranges.
Does anyone have a question?
Yeah, I have a question. So there was a slide where you showed the performance on the cassava leaf dataset, and I saw that for the Wikipedia text, it was underperforming for 5 to 10 shots, and then suddenly on the 20th shot, it took over the other pre-training datasets. Is there a particular reason for that? Yeah,
Is
that one, the box plot. The next one, I think there was a box plot. Yeah, right over here in the 20 shot fine-tune accuracy. For the cassava leaf, I think for the other datasets, Wikipedia text was underperforming, but for cassava leaf, it performed the best, I think. So is there any particular reason?
That was a nice observation. I haven't noticed this until now. I don't know what's happening there. Wikipedia is it's doing some magic here, because Wikipedia is far away from other data sets because it has many texts and some noisy images compared to others. I don't know what, maybe we looked at what's happening here on 5 shots and 20 shots. Like, see, for 10 shots, it's not the last one. Yeah, it is it's the last one.
It is the last one.
But for 20, it flips. I really don't know what's happening there. So flipping could be happening because, as just mentioned briefly, when you have only 5 or 10 samples per class out of 3,000 in CASA-LIF, that could be a bit challenging for transfer learning and stuff like classification to solve it. But you have enough samples, in this case, 20 samples, then Wikipedia showed its power. And I should say that if you have more and more, because we have enough samples, maybe 100 shots, then Wikipedia should be still better. But before 20 is not reliable, I would say, for the case of CASA-LIF, but after that it is.
But the performance should have been the same across the other datasets like DDD, Caltech, PITS. I mean, if it should not be exclusive to CASA-LIF, right?
Why not? Like CASA-LIF, what was this? CASA-LIF, that was these leaves, right?
Yeah, for 20 shots, WIT, Wikipedia text is the best performing dataset.
Yeah,
pre-training dataset, but for camera traps or clipart or any other dataset, it's the worst one. So
yeah.
like,
So
it's
correct
a
me
bit
if I'm wrong, but
inconsistent.
you're going to say that like Wikipedia was the worst dataset for the other dataset, except for CASA-LIF, which was the best.
Yeah.
And you're surprised why?
Yeah.
And I don't see any reason why such thing couldn't be happening, because Wikipedia, for some reason, is closer to CASA-LIF. It might be closer to CASA-LIF. That's why it's better.
Thank you for the answer.
Yeah. And my point was that it's not only for 20 shots, it's probably for 20 and onward until 3,400.
Yeah, like 100 or 200 samples.
Yeah, that would be the case. And Wikipedia just noticed that Wikipedia is not, I thought that Wikipedia is the worst, but it's not always the worst. Like for CASA-LIF, it's almost the best.
Hello. Can I ask 2 quick questions? Thanks for your talk first. So the first one is like when you measure the performance and about like different pairs of the pre-trained data set and then the test data set, do you actually measure like how similar they are? In terms of their like semantic or something? And then I expect like if they're similar, then maybe like the performance will be better, like just because of the similarity. And then the second thing is I'm very curious, like when you're doing all these pre-trained data set, do you have an experiment that actually like if we don't do any few shot learning at all, and then just evaluate using the pre-trained models, using the pre-trained models features, and then cluster them, and then to see like, I mean, to get those features from the test set, but use the pre-trained models, and then use them to evaluate the completely agnostic performance. Yeah, is that going to tell us like which model actually have some kind of pre-knowledge about the test set? Thank you.
Yeah. So regarding the first question, we haven't done, and probably you should do this. Like, of course, we had some, after a lot of experiments, we had some observations, and now we have some intuitions on the similarity, as also literature said. But we never quantified such similarities between pre-training and downstream. But it seems that, as been said in the literature, it's important, the kind of similarity, as I already showed, like red caps on pets on both text and visual domain. Regarding the second question, so we already, so the case of, for the case of this paper, we were interested on transfer learning performance. That's why we did it on few shot. But of course, you could do this zero shot, as OpenAI already did. Like everyone talking about CLIP mostly talks about zero shot inference accuracy. Or as you just suggested, we can use like KNNs, clusterings, to have at least some intuitions which dataset or which pre-training features are more closer to the downstream task. So short answer is, of course, it's possible. And I guess people in the literature already did this on zero shot or without doing fine-tuning. But for the case of this paper, we were interested in fine-tuning. Why? Because practically you will do this, right? Ultimately, you will not save some resources because you do not want to fine-tune. Ultimately, in practice, you have some samples on the at your hand, either 1 samples per class or 100, and you will do fine-tuning. And of course, fine-tuning would be the best case. Our question was that, given practical experience, which pre-training is the best? And we are going to answer this. That's why we emphasized on fine-tuning. But again, it's always possible to do this KNN or clustering to find out which one is better.
Okay, thank you.
Sure.
We have 2 people asking in the chat what tool you used to track all your experiments. Is it just spreadsheet or some ML ops tool or ML flow? Do you have any suggestions?
First of all, that was many experiments. I used Caliban, which I guess it's not, I'm not sure if it is still supported by Google, but it's still working. So Caliban helps me to run experiments because I need to take care of many experiments. I was using Google credits thanks to my collaborators. And I ran many experiments using Caliban. So Caliban is running either locally or on GCP, Google Cloud Services, and you could submit jobs. That was for taking care of submitting a lot of jobs because I need to train a lot of models using a lot of parameters, hyperparameters, learning rates, architecture, etc. That was for Caliban. And I was using, I totally forgot the name, the most famous one. What is the most famous experimental? MLflow and weight and biases. Yeah, I was using weight and biases for capturing the results.
Thank you. And
but I found Caliban really useful. You could do this also locally. You do not need to have Google credits. If you have 1 or 2 GPUs, whatever, you can do this on your local machine. And the most power is to run jobs and to take care of hyperparameters. You can get create a JSON file, and the Caliban will read each parameters like learning rate, like 5 learning rates, batch size 10 different batch sizes. And Caliban will take care of running 100 different jobs sequentially or in parallel if you have enough GPUs.
Thank you. This might be the most important takeaway from this talk.
Yeah.
I've stayed this long to hear this, and thanks for those sharing the link in the chat. Any other
Okay.
questions?
I guess there is no other questions, right? Yep.
Mm.
So thank you everyone for joining us today.
Yeah, thank you for coming again. And of course, anytime you have a new paper work, feel free to come and teach people.
Of
Or
course,
like
thank you,
people
Rosanna.
that used to track your experiments.
Yes, thank you for inviting me.
Oh, thank you.
Have a nice day, night, everyone. Bye-bye.
Have a good weekend.
You too, bye.
Bye.